In this example, we're asked to calculate the Joule-Thompson coefficient, mu, for a van der Waals gas. This is the definition of mu, dt dp at constant h. P versus V and T is given here, and this is the van der Waals equation of state. This problem is a nice example of the utility of the cyclic chain rule. I'll show you in a minute. Notice that the Joule-Thompson coefficient is a relationship between T, P, and H. So we want to know how T depends on P at constant enthalpy. And it may help to write the following cyclic chain rule: dt dp at constant h times dp dh at constant t, dh dt at constant p equals -1. And notice that this is mu. This is what we're trying to find. This is the definition of heat capacity. So if we can find this quantity, then we will be home free. Let me rearrange a little bit. This means mu is equal to minus dH dP at constant T divided by Cp. And in order to get dH/dP at constant T, I'm going to use the following fundamental property relation. And I'm going to divide through by dP and hold T constant. T ds dP constant T plus V. Again, remember, well, not again, but dP over P, or dP over dP is 1. This is related through a Maxwell relation to dV dt at constant P. And I'm going to use another cyclic chain rule, in this case in terms of P, V, and T. And the reason, notice that, so if this were the ideal gas law, it'd be straightforward to calculate. You just have to express V as a function of P and T, and you could calculate the derivative. However, this is a cubic equation of state, which would make it kind of hard to calculate V. It's a little hard to actually come up with an explicit solution for V. It would be much easier if we could calculate the derivative we want in terms of derivatives in pressure, because we've solved for pressure. And let me show you that we can do exactly that. So we have dV dt at constant P times dP dV at constant T times dt dP at constant V equals -1. And so what this means is that this term is equal to dP dt at constant V divided by dP dV at constant T. So we can solve for those things by taking derivatives of this expression. Let me copy it over. With respect to T and V. So let me write this a little more simply. So we're looking for ds dP at constant T, and we determine that this is equal to dP dt at constant v divided by dp dv at constant t. This must be equal to, so here the temperature derivative is just R over V minus B, R over V minus B, and then the volume derivative can be taken, minus RT over V minus B squared, plus 2A over V cubed. So now we can plug, so what we're looking for is dH dP at constant T. Well, actually, we're looking for the Joule-Thompson coefficient, which is minus this divided by Cp, but dH dP at constant T is going to equal this expression times T plus V. So RT over V minus B divided by minus RT over V minus B squared plus 2A over V cubed plus V. We can simplify this a little bit if we want to. We can say V equals, or that's equal to V plus RT over V minus B times V cubed divided by 2A over V minus B squared minus RT V cubed. Yes. So the last step is to calculate mu, which will be minus 1 over Cp times this quantity. And that's the answer we're looking for.